Okay, so if you look online in today's folder, you'll see there's a set of set of homework problems, take-home quiz problems that are due on Friday. And then on Wednesday, there's another group that's going to be due next Monday. And on Wednesday, we'll start with a quiz where I will give you a table of 10 blanks. One of them will have hydrogen in it, and you'll have to put the groups in, numbers 1 through 10, and then tell me whether the group is activating or deactivating, by resonance or induction, and whether it's an ortho-para director or a meta-director. So it'll be a big table that you'll have to fill out. So if you haven't started learning that table yet, you need to by Wednesday. And then you need to hold on to it for the rest of the semester. Okay. So here's where we're at. And again, it'll be mostly... This is going to be mostly in lecture just because we're at that point in this semester. So last time we started with the idea of we're going to take a benzene ring and we'll put a methyl group on it, so we'll start with toluene. And we're going to react that with HNO3, H2SO4. And so when we do this, the first thing we need to do is we need to say, okay, what is our electrophile? And our electrophile in this case is NO2 plus. So that NO2 plus is going to add to the ring, but it doesn't self-direct, it directs according to where the methyl group goes. So I need to know for the methyl group, is it an ortho-para director or is it a meta-director? And you would say it's an ortho-para director because it's an activating group. It's number 3 on the list. So that means it's going to direct ortho and para to itself. And so we're going to get 2 different products for this reaction. We're going to have the nitro group added ortho, and we're going to have the nitro group added para. And I'm going to go ahead and I'm going to use the circle for these reactions because it's just a little bit easier to do. So that's straightforward enough if you know the chart. So it's the methyl group that's going to do the direction of the nitro group. But what happens when I have more than one group on the ring? Basically, who's going to direct? And the way the Top Hat book does this is, well, honestly, it's the way I used to do it for probably the first, 7 or 8 years that I taught, where I would say, okay, let's look at the 2 groups. So let's add another nitro group to this. Let's add another nitro group to both of these, basically, as my example. So where is the NO2 plus going to add in the second type of reaction? Well, the way to do this is, the way we can think about this is, if they're both the way the book explains it, if they're both activating groups, the group that's more activating is going to be the director. If one's an activating and one's a deactivating group, then the one that's activating is going to be the director. And if they're both deactivating groups, then the one that's less deactivating is going to be the director. And so honestly, that's the way I used to teach it. And then one day in class, and I know I can remember exactly the student that did this because they're now like a physician down at Akron Children's Hospital. And she raised her hand. She said, "Do we really need to do that? Why don't we just take the one that's highest on the chart?" And I said, well, that's a pretty genius idea. So we can cut out all of the is it activating or deactivating and just simply say, okay, which one has the highest number? And this chart should really look like this. And this is the one sheet of notes last week that I handed out, I think, on Friday. And if you didn't get those, I rearranged things so that I don't think I have them on my card. So really what we're going to do is we're just going to compare who's the highest on this chart. They're going to be the director. That's why you need to know the chart. And honestly, that's the way I've taught it ever since. So, if you don't think you can actually suggest something that'll be helpful, you can. Because that did, and I had never thought about it that way up until that point. Apparently, the people who wrote the Top Hat book were never asked that question either. So it's just easier to say, okay, which one's the highest on the group? So in this case, it's going to be which one? Methyl or nitro? Say it. It's going to be methyl. Up here, methyl versus nitro, which one's highest on the chart? What? Highest on the, not the highest number, but the highest in terms of, let me go back because I did number these, I guess, wrong. The one that's the top of the chart. So these are going to be the activating groups, and then here's your deactivating. So which one has the lowest number, right? Because that's going to be the one that's the most directing. And in this case, it's going to be methyl or nitro.
Methyl.
Thank you. It's methyl. Wait, methyl's not on the chart. Yes, it is. Okay. So, yeah, the one with the lowest number is going to be the one that does the direction. The one that is the most activating, and if it's deactivating, that's the most less deactivating. Okay, so that's how we would do that. So the methyl group is then going to direct ortho and pair it to itself. So that means I'm going to end up with the nitro group here as one product plus the nitro group para as the other product. If I do that to this molecule, the methyl group is just going to direct ortho to itself. If there's already a group at the position it's directing to, you can't kick that group off. So in that case, in the second case, there's just going to be one product, which is to put the NO2 group there. Well, and then there's the NO2 group there. Okay. And you might say, Carolyn.
So, like, for the first product, who's in that, like, 2 position next to the stage 3, right?
Like this. You can't have two NO2s attached to the same carbon. No. Because remember, the circle represents single bonds. Or circle represents the alternating single and double bonds. If I have two groups attached to that, I can't have a double bond there. Now you might say for this one, well, what about this? And what's the relationship between these two molecules? They are the same. They're the same molecule. So whenever you're going to get the same molecule, you only have to write it once. Okay. And actually, if you write the same molecule over and over again, you're not going to get any additional credit. I used to probably take points off for that, but maybe I won't do that this time. But you got to realize you're not making a new product. So in this case, they're the same. And then, if I wanted to, I could react all of these products with one more equivalent of HNO3, H2SO4. And if I did that, what I'm going to end up with is the final product, which is this molecule, which is 2,4,6 trinitrotoluene. And I show this one as an example because this is trinitrotoluene. Right, which more accurately would be what would be in a stick of probably dynamite.
Because the nitro groups go from solid to gas.
Yeah, the nitro groups are basically an embedded NO2 gas molecule. So that's how we've said when we've had those molecules like peroxides in the past, that's going to be the problem. This is, I think trinitrotoluene is when you make a dynamite stick, and you're not going to make a dynamite stick. But if you were like working for the Nobel company, which that's what Alfred Nobel did, was find a way to take TNT, put it with clay in a stick so that they could make dynamite out of it. What you would end up, you have to stabilize it with clay or something like that. A dynamite stick is not just pure trinitrotoluene. But that's how Alfred Nobel he set up a company, and they made a lot of money. They blew up a lot of family members in the process, because if you think about this process, every time I put a nitro group on the ring, I'm making the ring less activated. That means I got to heat it. And there's going to be a fine line between heating it to get the nitro group on the ring and heating it to explode it. And so sometimes if you cross that line, it explodes. So in the end, this is part of the reason why Alfred Nobel set up the Nobel Peace Prize and the Nobel Prizes in medicine and chemistry and all of that when he passed. So it was because of the fact that he was generating something that was he considered, I guess, to be, I don't know, you could call it a weapon of war, right? But everything is nowadays. So that's where Nobel made TNT. He didn't make nitroglycerin. Nitroglycerin's another molecule altogether. And I think probably I called cousin Alfred Nobel because he's like the sixth cousin X number of times removed from my great-grandfather. But if you have any Swedish heritage, you're going to have a relationship with Alfred Nobel because it's a small country. So, needless to say, no money transferred down the line. No fame and fortune either. So, this is the best example of how we can do multiple electrophilic aromatic substitutions, and we're just going to follow that. What would be the major product of this reaction? The first question is, what's my electrophile? Br plus. We agree with that? Okay, I guess we all agree with that. Br plus. Now, where's Br plus going to add? And I put letters on here to kind of, we could make this a multiple choice test, exam, if we wanted to. We won't, but could. So, is the BR going to add to A? How many people say yes? B, C, D. So most of the hands were for A and C. Actually, the most hands were never lifted off the table. So who's the director?
NH2.
NH2 because it's the number 1 group. So it's going to direct ortho and para to itself. So that, the first thing we do is we just basically copy the molecule over again. And so I'm going to add a BR there and a BR there. Are those the same products? Same products? No? Okay, so they're different products. So we would get both products. And honestly, it's as straightforward as that. But there's a lot of things you need to know. First thing you need to know is you need to know how to generate your E pluses. And then once you generate the E plus, you need to know your group so that you know which one is the director. So I didn't say it was easy. I said it was straightforward. Because if you don't know either one of those two things, it's not going to be easy or straightforward. Okay? So that's why we need to take the first step to remember and learn all of those groups. All right, so then that's what you need to know. Let's see if I've got, okay, I've got one. How about this one? All right, everybody got an answer? Okay, let's see. Table number 7. 1, 2, 3, 4, 5, 6, 7. Either Sarah, you or Olivia, or both of you together. Question number 1. What's the what's the electrophile? NO2 plus. Table 6. Where's the NO2 plus adding? That's you guys. A? Do we agree with that? That the NO2 plus is going to add A? I think they agree. I'm not sure. Does everybody agree with that? Does everybody know why we're adding to A? So that's an OCH3 group. It's an O. So the O attached to the ring is activating, and so that's orthopara. But there's a chlorine in the para position, so we only add to the ortho position to it. So we're adding to A. Okay, last one that's going to illustrate something. Bless you. So, in this case, what is the electrophile that I am generating? Let's see, table 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sadly, Nicole, you're all by yourself. So what's the electrophile? Joe, can you help her? CH3Cl AlCl3. Can somebody help her? Jacob. Do we agree with that? So whenever you have an alkyl group attached to the chlorine, it's going to be that alkyl group becoming a positive charge. And if it can rearrange, it will rearrange. So this is an example of what's the name of this reaction?
Friedel-Crafts.
It's a Friedel-Crafts alkylation, right? This is Friedel-Crafts alkylation because I'm going to add an alkyl group. Okay, so we got a CH3. Of the bromine and the nitro, which one is the higher on the chart? Let's see, 1, 2, 3, 4, 5. Abby or Kristen? Bromine's higher on the chart. Agree? We agree with that? Okay, so the bromine's going to do the direction. Table 14. Oh, there's nobody at table 14, sadly. Table 4. Let's see, my question's going to be, where's the bromine going to direct to? Bromine. So bromine is deactivating, but remember, it's the exception to the rule. Ortho-para. So it's going to direct ortho and para to itself. Bromine is a deactivating group, but it is the exception. Okay. So we have to make sure that we remember that. So that means bromine is going to direct ortho and para to itself. Now, I'm going to throw an additional rule here. And the additional rule is that there are places we never add. And we never add in between ortho-meta groups. We're going to never add in between two groups that are meta. Okay, so we're never going to add between meta groups.
Ever anything, because I'm guessing that has to do with size.
It's going to have to do with sterics. So while you
small enough to add?
no,
Okay.
no, you'd think that there might be enough room to add something small, but what would you think is small?
The hydrogen.
Yeah, we don't add hydrogen to the. We don't add an H plus to the benzene ring. It's got to be everything bigger than an H plus. You think a methyl group is small? Nah. Bromine is small. Now, methyl and bromine are about the same size. So the thing is, when you have a 1,3 disubstituted, there's just not enough room here to add a group. And so we never add in between meta substituents. That's the rule of this. And there's going to be times when we're going to invoke steric hindrance to even say, oh, well, that electrophile is going to add only para and very little of it's going to add meta, but not right now. So right now we're just going to say you never add in between meta substituents. So in this case, the only two products that you're going to get is to add the methyl group or para to the bromine and ortho to the bromine. And notice how when I wrote the products out, I just replicated the molecule and then I added the two groups. So let's see, next Friday is our next test, right? I think it's the end of the month. So if you're scrounging for points and you have one of these problems, you can write the molecule in exactly the same form it is, and then you just have to make sure you get your electrophile in the right place. First, you got to make sure you got the right electrophile, and then you get it in the right place. So I guess it might not, guessing probably isn't going to work very well. Unless you're super lucky. All right, so that's what we need. We need to know our electrophiles. We need to know how to add them. That's what the problems that are due Friday, that's what the problems that'll be due next Monday are there for. And there are more practice problems in the folders because I went and I moved everything that I had as practice problems, chose one of them to be graded, and then some of them to not be graded. There is a humongous set of problems that you can try, but they won't make any sense until we do the next part. All right, so is everybody okay with this? two things you need to do: find the electrophile, and then find the highest group on the chart, the one with the lowest number, and that's going to do the direction. And don't add in between 1, 3 substituents or meta substituents. Now let's talk about working backwards. Because these are the kinds of problems that really work well trying to synthesize different molecules. So when you're asked to go from benzene to a substituted benzene, how am I going to solve this problem? You tell me. First step, what do I need to know? Jacob.
You need to know the reagents to add.
And reagents to add the NO2 group. So what's the reagent? What reagents do I use to add the NO2 group?
HNO3 and HNO4.
And how would I add an ethyl group? What do I want to use?
ClCH3 and then HCl3.
So I want to do Friedel-Crafts alkylation on that one. So that's the first thing you need to know is what reagents do I add? And then I need to look at the substitution pattern between those two groups. So in this case, I'm going to add HNO3, H2SO4, and then ethyl chloride and aluminum trichloride. Which set do I add first? Table 10. I have a suspicion table 10 is you, Joe. You gonna add the ethyl group first? Okay. Table 17, which is, how many tables we got? How do we have 18 tables? Oh, we have 4 tables. So, which table is 17? Oh, look at everybody just pointing away. It's the table that's not theirs. I think, Melanie, that's you. That's who they were pointing to. You can yell at them afterwards. So you and Joe's... What?
There's 4 rows of 5. So 15 said 15.
That is true, but how did I only put in 18? That means that somebody who's in 19 and 20 are never going to be called on. We'll change that in a minute.
Well, unless you can't count those tables.
No, I counted those tables. What I need to do is I'll print out a set of cards, and we'll use cards we can use a top hat system to answer these questions, but I was going to print cards out, yes. Anyway, what's your choice? 17 would be you. What do you think?
Whether it's ethyl or NO2 first.
Right. Which one's first? Which group do you want to add first?
NO2.
Okay, so we're split, 1 and 1. Table 11, David. NO2. 13. Aisha, Colin. NO2. Okay, so we got 3 to 1 NO2. Why would we want to add NO2 first? Aisha?
Because they're meta.
Because they're meta to each other. So So it's not really a random choice. What we have to do is we have to look at the substitution pattern. If I add the methyl group, or if I add the ethyl group first, where's the next group going to go? It's going to go ortho and para to itself. If I add the nitro group first, where's the next substituent going to go? Meta to it. So we have to take that into account as we're deciding order. So in this case, HNO3, H2SO4 would be first, and then CH3, CH2, Cl, Al, Cl3 would be second. So that way, when I form the nitro, when I add the nitro group, then the nitro's directing the ethyl group. So it's not just a random choice. We've got to decide given the substitution pattern.
So say that you did this, like you added the CH2, CH3 first, and then the NO2 had to be ortho and para to itself. So then you would have two different products there because the one wouldn't be.
Right. So I wouldn't be making the product I want to make.
Okay.
I'd be making a whole different product. So when we think about doing these multi-step problems, we really have to think about the substitution pattern and how to get the groups to add the right way. Okay. Now, we have kind of a limited set of reagents here. You may think it's a lot, but it is kind of limited. So here's some other things here's some other ways to put groups on the rings that we don't know about. Well, you know what, we do. We just haven't thought about it. So do we know how to put an SO3H group on the ring? Yes, how? SO3 and H2SO4 will put an SO3 group on the ring. If you're kind of sitting there going, I need to know the reagent that fast, that would be helpful. So there's a lot of stuff here. In addition to the chart, it's not just the chart, it's also the electrophiles and how we add them. Do we know how to add a COOH group to the ring? Jacob? Okay, we might as well destroy this reagent right off the bat. No. Okay? You might think that we could do Friedel-Crafts alkylation with this half acid. No, I shouldn't say it that way. This half chloride from a carboxylic acid and a carboxylic acid. But this reagent is very unstable if I was to make it, and that's if I can make it. So this reagent actually is not allowed. I'm forbidding this reagent to be used because it's not stable. And actually, you'll see another example later on where it's not stable as well. So we can't do that. So the answer is yes, we still know how to put a CO2 on the ring, but it's not something that we've covered. Well, it is something we've covered recently. Two methods. There's two methods to put a CO2 on the ring. Not in one step, though. And I'll give you the pattern. There's the two steps. How do we put an alkyl group on the ring? Friedel-Crafts alkylation. So if I put an RCl, AlCl3 on the ring, I'm going to put my alkyl group. Now, how do I convert my alkyl group to the CO2H group, to the carboxylic acid? It's not like we didn't do this in lab 2 weeks ago. So my hint would be it's purple. KMNO4. So if we oxidize any alkyl group, we're going to get a carboxylic acid. Okay, so there's method number 1. Here's method number 2. Put a bromine on, make a Grignard out of it, and then convert the Grignard to a carboxylic acid. What reagent should I use? Your choice, or your reaction. You can call the reaction you'd like. Table 5. 1, 2, 3, 4, 5. That's you guys. Or no. 1, 2, 3, 4, 5. Abby and Kristen again. Any of those reactions? So BR2 and AlBr3. Okay. That's the first step. Table 11. That's you, David. You can call either of the next 2 reactions.
Then you just stay.
Okay. So we add magnesium to make the Grignard. 15, 10, 11, 12, 13, 14, 15. Nicole. Do you remember what we add to a Grignard to make a carboxylic acid? They left you the toughest one. Need help? Melanie? CO2. CO2 and then H plus H2O. That's the toughest one to remember. So Grignards plus CO2 and then H plus H2O gives you the carboxylic acid. So these are the 2 methods that we can use to add a CO2 to the ring, or CO2H to the ring. So now we have to go back and we have to remember those reagents because we're going to use them here. So you can't add a CO2H to the ring in one step. Now, let me point out a couple things here. In this case, I'm asking for meta substitution. But what if I was asking for the SO3H group to be para to the COOH? You might look at that and go, wait, both of those are meta directors. How do they end up para? Jacob?
Well, can't you add the SO3H group to one of the intermediates, so to add in the COOH and then finish the reaction?
So in other words,
When you have the R attached.
or the BR. So what we want to think about here is that in these 2 syntheses, the R group is an orthopara director, as is the bromine. So if I need to have the 2 groups orthopara to each other, I could add the SO3H group to the alkyl benzene and then oxidize the alkyl group to a carboxylic acid. So there are times when we're going to need to add the group when we're going to get the right substituent, when we're going to get the right substitution pattern. So in this case, these are groups that kind of switch. So in between it's orthopara, but then at the end it's meta. So that we can decide to do that. The only thing we have to be careful of is that if I want to oxidize the alkyl group, that whatever group I put on the ring, I don't oxidize as well. So you have to be careful of that. And if I'm going to make a Grignard, there better not be a protonatable or a proton or a hydrogen that's acidic on the ring, because the Grignard is going to immediately remove that. Right, so here's how to add a carboxylic acid. Now the other reactions that we can do are to convert some groups into other things on the ring. The biggest group here, well, the biggest one to the first step, I guess, to the biggest collection is to reduce a nitro group. So when you have an NO2 group, you can reduce it to an NH2 group by using iron or tin, HCl, and heat. So the next series of reactions that we're going to talk about on Wednesday, after the quiz, is adding groups to complete the chart. Because how do I add a C triple bond N group? That's going to require us to use what's called a diazonium salt. And so there are some groups that I don't quite know how to add. And how do I add the NH2 group? By reducing a nitro group. How do I add an OH group? That's going to come from a diazonium salt. And so on Wednesday we'll talk more about this. We'll kind of finish this up. And then we're going to go into some organometallic ways that people really do these reactions. Things like what's called Suzuki coupling. We'll go back and talk about lithium cuprates and Gilman reagents. And also then there's Suzuki, there's Heck, there's all sorts of things that we can do to actually add any alkyl group I want to the ring. And this is actually how synthetic chemists really work, is a lot of these organometallic reagents. And so those are actually in your textbook as well. And so I'm going to go over, and I'll go over those. I'm still trying to get caught up here, but when I lecture, I don't quite totally get caught up. So, but that's what we're going to be doing on Wednesday. So we'll start with a quiz, and the problems that are online or the problems that are in the folder are due on Wednesday. If you have any questions, come and see me.